for joining today. My name is Hashim Ali, and I'm a PhD candidate at the University of Michigan Dearborn. Yeah, I should have my camera on as well. So I'm advised by Dr. Hafiz Malik, who's a professor and dean at the Department of Electrical and Computer Engineering. And our lab is ISSF lab. It's Information Systems Security and Forensics lab, and we usually work in the space of cybersecurity and information security in this lab. So today I'll be talking about audio anti-spoofing, especially in the age of hyper-realistic audio deepfakes, and we'll be going over the competitions, the development of these systems over the years, and what really sparked the development. So we'll be going over the challenges, data sets, and what kind of challenges these systems face these days. So meaning robustness. So here. So let's just first discuss what is a deepfake. A deepfake is any synthesized digital media, image, audio, video of some person of interest using some machine learning tools. So today, deepfakes are simple to make, and they can be extremely realistic these days. And these days, deepfakes are becoming like more and more catalyst behind misinformation and disinformation campaigns on social media platforms and other social networks as well. So very broadly, you can divide deepfakes into two broad categories. One category is someone generates a synthetic content by standard text to speech or any other generation tool, but it's not targeting anyone. So this content is not targeting anyone. Like for example, these days we use ChatGPT, and we use other like we use Siri as well, and so they have generated content, but they're not targeted to any one person or one community. But there's one more type of synthetic content generation in which you are targeting one person or one community. For example, if you generate an audio of in the voice of President Biden, now you're targeting President Biden, and now you're making him whatever say that you want. And in general, deepfakes have a negative connotation, because the term deepfakes is considered very like negatively, but it's essentially like synthetic generation, and there are benefits to it as well. And then there are there are like harmful scenarios in which deepfakes can be used. So let's see like how deepfakes are impacting society. So so these days, deepfakes are used for multilingual voice AI voice dubbing. For example, someone can generate AI generated voices using like automatically and they can automatically dub films, lectures, and educational content into multiple languages while preserving the tone and emotion behind the original person. So these days, these deepfakes are used in films and TV and digital recreation as well. Like studios, for example, they can use synthetic voices to create, for example, historical figures, and they can de-age actors as well. And so they can essentially bring digital characters to life, and then they can revolutionize storytelling and production efficiency as well at the same time. So these deepfakes are also being used in accessibility and assistive technologies. Um, so, for example, if someone has speech impairment, they can use these synthetic voice in their like natural voice, and they can communicate as a natural person. Um, Similarly, some people who have trained machine learning models, they know that these tools that we use to generate synthetic content, they are extremely used for training and data augmentation of these models. So there is the use there as well. So now there are like a few bad use cases of deepfakes. So bad use cases of deepfakes are in which you are impacting like only a single person, not the whole community. For example, you use deepfakes to do corporate and financial scams. And for example, recently there was like around $35 million were stolen in Hong Kong by using a clone voice. You can use these deepfakes to attack someone's identity and their reputation. Like for example, you can generate voices of journalists, public figures, or even private people as well. And this deepfake technology is also used for unauthorized voice cloning, for entertainment, dubbing, and parody purposes as well. And then you can use this, and it's already being used. That you can create like non-consensual deepfake pornography of people without their consent. And then you can impact celebrity and influential person as well. And then you can use the same technology for pranking and harassment purposes. But essentially, the bad cases are generally where you are targeting only one person in the community. And now there are like extremely bad cases, which are ugly cases of deepfakes. So in which you are impacting the whole electoral process. Like for example, in 2024, there was a Biden robocall in which he was telling his voters in New Hampshire to abstain from casting any votes, right? And similarly, there was an incident in London in which Mayor of London, Sadiq Khan, was targeted, and he was essentially in that audio. He was telling people to incite hostility during the Armistice Day. And then similarly, if so these days, banks and other financial institutions are also using speaker verification systems and other biometric systems. And if these systems can be compromised using deepfakes, so there is the impact there as well. And we can people are also creating deepfakes of warfare scenarios. For example, there was a video of President Zelensky back in 2022, in which he was saying his soldiers to lay down arms, um, uh, and accept the defeat. So, but the at that time in 2022, the deepfakes was very naive, and people instantly recognized that this is not true. This is not real. It's something synthetic. So let's discuss why audio deepfakes are important, and why are even more important than video deepfakes. Let's say so these are like a few examples of video deepfakes. And the first one, it's Tom Cruise, and so it's a Tom Cruise mimicry, and this guy has like a whole channel. Can you guys hear it?
The audio is not coming through.
Oh, okay. Let me see. I'm not too sure. So, anyways, so essentially, like my point here is that so this Tom Cruise video, you will be able to see some inconsistencies in his facial landmarks, and the same case for Donald Trump. So you can see the his lips, and you can see instantly there that there is some inconsistency there in the time frames. So let me for this only, let me stop sharing my screen. Share my screen from here. So can you guys see my screen?
Yep.
Okay, sorry for the interruption. So essentially, this example actually needed the audio. So so let's hear this audio of President Biden.
A bunch of malarkey. For the November election. We'll need your help in electing Democrats up and down the ticket. Voting malarkey. We know the value of voting Democratic when our votes count. It's important that you save your vote for the November election. We'll need your help in electing Democrats up and down the ticket. Voting this Tuesday only enables the Republicans in their quest to elect Donald Trump again. Your vote makes a difference in November, not this Tuesday. If you would like to be removed from future calls, please press 2 now.
So so this was essentially a deep fake, and it was the same example that I showed earlier. That this deep fake audio was sent to people in New Hampshire, and he was essentially telling people to not vote for him during the primary elections. And here's like a more like kind of a funny example of.
Hello, my Pakistani American friends. I promise if I win, I will try my best to get Imran Khan out of jail as soon as possible. He is my friend. I love him. I will support him to take over the government again and rock, and we will work together to make our ties stronger. Imran Khan, zip.
So he was like, so the prime minister was of Pakistan was in jail, and so this audio got like really famous, and people actually believe that so that he actually said it, and but essentially it was deep fake. So the more so when you take a look at the two examples, like video deepfakes and audio deepfakes, you'll see that you can instantly spot that there are inconsistencies in the video. There are like temporal inconsistencies. There are like sometimes facial landmark trajectory is not continuous. So you can spot that something is wrong with it. But in the case of audio, you have much less information density, and you are in the case of video you can see the video, but in the case of audio you can only hear it, and even we can only hear like in certain bands, certain frequency bands, and so that makes it much more difficult to spot whether the audio is fake or real, unless you know that how this person talks. If you know someone very closely and you know how that person talks, only then you'll be able to spot the deep fake. Otherwise it becomes very hard to spot it. So so let's discuss the evolution of this hyper realistic audio deepfakes. In the 90s, there was the technology that was used was concatenative synthesis methods. So this in this method, people used to have voices in a database, and then they would just concatenate those voices together, and those voices were essentially recorded by voice actors, so they were not actually synthesized. But then in around 2000 to 2010s, so this statistical parametric synthesis came. In this method, people started creating acoustic models to parameterize the voice, but this technology was still not that good, and people were using like HMM based acoustic models at that time. And but still the voice was very like robotic, and the quality was not that good as well. So moving forward to around 2010s to 2020s, people started using neural networks to synthesize voice. And so here, like, neural networks actually made a difference, and we started getting much better voice quality, much better um, real like human like sounding voice. But there were still inconsistencies. You were not able to generate like longer voices, and every now and then there will be some noise in there that you can spot. Okay, so this is not actual real. So, but then in the last 5 years, so much happened. So diffusion models came. We were able to generate much better voice with much better quality. And in that same time frame, people started using codec-based synthesis as well, in which they created they encoded audios using language models, and they use those models to generate the synthetic voice. And then at the same time, within the last 2 years, LLM based synthesis came as well. And the last three were like equally good, but they use like different technologies. So essentially the difference between this and the last one is you are able to create like synthetic voice with only a few samples of someone's audio. With diffusion models, you need like more samples. You need like at least a few hundred samples of someone's voice to clone it. But with LLM based synthesis, you can just have 3 seconds, 4 seconds, 5 seconds of audio, and then you can clone that audio as well. So that's why, like, 11 Labs and these companies have come up, where you can just upload a few samples of your voice, and then you can instantly create your own synthetic voice model. So having discussed that, the evolution of the synthesis, let's discuss like how audio authentication works. So audio authentication is you create like you collect audio samples from multiple people, right? And then you train a model. That model will extract features, and then it will have some classifier, right? And then this model will be trained to identify these people, right? And when a test audio comes in, it will take that audio in, and then it will tell whether that person is that person, or whether the test audio is actually that person or not, right? So this is this is a very generic audio authentication pipeline that people have used, and it's audio authentication, speaker verification. They have been used interchangeably. So this audio authentication pipeline, or this audio authentication system, is vulnerable to many threat vectors. So first threat vector is what we are discussing today, is like you can create synthetic voices, right? You're using these extremely good deepfake generation technology, and then you can pass this to audio authentication. This audio authentication will fail, and then we'll not be able to identify that if that person is real or not, right? Or in the case of um, if the system is kind of mimicking some person, and this system is able to detect that person, then the system will give access to this person, right? Whose deepfakes were generated. So this is kind of a deepfake threat, but so people were able to create safeguards for deepfake technology that were present at the time. But then what happened was people started adding some kind of noise or laundering attacks to the deepfake generated audio, and then passing those voices or audios to the underlying audio authentication system. And then again, this addition of noise tipped off this audio authentication system, and it again will give access to the person trying to get access. And then the other problem in this domain is so this, for example, the safeguard that you have developed to protect this audio authentication system is trained on a few older deepfake generation methods, and then the new methods came in, and those methods were unknown to the protection mechanism, and maybe those so this maybe the new methods have different languages or unknown post processings. So again, when you do all these kind of processings, you will again be able to give access. The system will give access to the person who's trying to get access, the bad actor. So having realized that you have an anti-spoofing system, right? And this anti-spoofing system is vulnerable to laundering attacks, noise, like real-world processings, and this anti-spoofing system is also vulnerable to unknown generation methods as well, unknown TTS methods as well. So so let's discuss like how audio anti-spoofing methods, how deepfake detection methods um, became better over time, were evolved, right? And this evolution of anti-spoofing is very centered around the competitions that the community held over the years, right? So we call these competitions challenges, right? And the improvement, the progress is centered around that. And you will see like even the databases that were introduced were very closely linked to the challenges. So the first challenge, the first competition that was held was around 2015 to 2017, and this challenge was mostly this was the first benchmark, and this challenge was mostly considering the logical access attacks. So logical access attacks is also is just another name for the deepfakes. Um, so, but these deepfakes or logical access attacks were created using very traditional methods that were present at the time, right? And people were able to detect these deepfakes pretty good at that time. And then at the same time, so this competition challenge organizers, they also presented or created a database called ASVspoof 2015 2017, right? So every challenge has a database or link to it. So for example, so how it happens is they create the database, and then they share this database with the community, and then the community trains the model on the database, and then that same database will have some kind of evaluation data that's held out, and that's not visible to the developers, to the participants. And then the organizers will evaluate the proposed methods or the submitted models on this evaluation data, right? So this is the whole process, but with every challenge there is a new database, and that database tells us like where the trend is going. So then moving to ASVspoof 2019 to 2021. So at this around this time, so this ASVspoof 2019 challenge is very central to the audio anti-spoofing community, because this was the first challenge which used synthetic methods, neural synthesis methods, right? And so it has two versions. It has 2019 version, and it has 2021 version. And so 2019 version shared training data with the community and evaluation data, but that both the data sets were clean, right? Both data sets were recorded in clean environments, right? But then in 2021, the organizers tried to add some kind of noise, some kind of codec compressions on top of the audio to mimic the real world post processings, right? And so this was the trend after that. Um, so then came the ADD challenge around 2022 to 2023, and so this challenge was more like Chinese and English bilingual, and they also use traditional neural synthesis methods, right? And but they have another task, which is they try to uh, detect the segment level audio deepfakes. So they said that maybe you have an audio and there's only one segment of that audio is fake. So how would you detect that only one segment within a real audio, just one segment of the audio detection? So then you have ASVspoof 2025. This is very real, very recent, and they've used like multilingual audio sources, and this challenge was crowdsourced, right? So they have asked like the community to create synthetic voices, right, and then to share those voices with the organizers, right? And it also has laundered conditions, and they use kind of diffusion models and LLMs to generate their synthetic voices mostly. And then even more recent challenges is the safe challenge. So this safe challenge is kind of unique in a sense that they never shared any data set with the participants, right? And their purpose was to to assess the generalization of these submitted models on different languages and different DTS attacks, which the model hasn't seen before. And they also have these processed and laundering attacks as well. So over these challenges, you have different. There were other databases that were introduced around the same time, which are very central to the community. Uh, the first database is called In the Wild database. It came around 2022, and this database. So the authors of this database, they source the audio from real world scenarios. So they never generated the audio themselves. They just source naturally occurring deepfakes from the internet, right? And then they collect them together in the form of the database. So it's called In the Wild database, and this In the Wild database is very good, is very essential in evaluating the performance of deepfake models, so anti-spoofing models. So then we also proposed one database around 2023. It's called ASVspoof Launder database. So what we did was we systematically applied many real-world processings on top of the ASVspoof 19 database, right? We applied reverberation, resampling, recompression, noise addition, etc. And so the purpose of this database was to evaluate the one-to-one performance. Like if you have a same audio in the real case and then you add some kind of noise on top of it, how the performance degrades when you add that kind of noise on top of the same audio. So that's why we generated this database. And then there's another database that came around 2024, 2025. So this database, they used VoxLab1 database to create their data, and they used like many recent latest TTS systems to generate the voices. But their uniqueness was they source the data from real world scenarios to even train the TTS models. So previously, all the TTS generation was occurring on clean audios, clean voices, but they collected the voices from the YouTube, from other sources, and then they created the GTS synthetic speech. And then again, we recently proposed a data set called famous figures. So this data is more focused towards identity specific detection, deepfake detection. So we created audio deepfakes of 10 famous figures around Joe, which includes Joe Biden, Kamala Harris, Donald Trump, and Barack Obama. And then we created an automated pipeline that collects the data from the YouTube, and then we pass that data to the synthesis pipeline to create the synthetic speech. So our point of view was, so some people are much more vulnerable to the audio deepfakes as compared to other people, and we need to have, protection mechanisms for those people specifically in hand. And we used diffusion based methods and LLM based TTS models to generate the synthetic voice. So around these same challenges, these anti-spoofing models also were proposed. So for example, in around 2015 to 2017 challenge, most of the submissions were handcrafted feature based methods. So they in these methods you would have an audio, and then you compute some handcrafted features like CQCC or LFCC, right? And then you attach some kind of machine learning model with it to do classification. And then around 2019, people started using more supervised learning based methods, or they started using they started learning the features, right? For example, previously they would use handcrafted features, but around 2019 or 2021, they would learn the features using these deep learning models, and then they would either attach a deep learning classifier or with it, or a machine learning classifier with learned features to do classification. So then around 2022, the trend moved towards end-to-end learning methods in which so there was no feature extraction involved. So examples of such models are RONET2 and ASIST, and these end-to-end learning methods or models, they performed much better as compared to previous representation learning methods or handcrafted feature methods. So then after that, in the ASVspoof 5 challenge, the trend was to use more self-supervised learning based methods to extract features, right? So self-supervised learning based methods, so in this technology, people have around this time people have started created foundational models, and those foundation models are trained on huge amount of data set, and so these foundation models are claimed to have a very accurate representation of the audio, right? So then people started using these models to extract features from these models, and then they pass these models to either a deep learning classifier or a machine learning classifier to do classification. So examples of SL models is Wave2Vec, XLSR, Hubert, and WaveLM. So around the safe challenge timeline, people started fusing multiple models together, and they would combine handcrafted feature methods with deep learning based methods with the SSL based methods, and so there is a mixture of experts. Technology is also introduced around this time, and then there is also a trend towards diversifying the training data. They would combine multiple data set together to train their models to see how they perform. Okay, so so here if you guys have any questions right now before I move to one of our publications, one of our work, so please feel free to ask any questions if you have. Let's see. Do you have any questions? Okay, so we'll keep moving forward. So this work is is the same work that I mentioned earlier. We developed a database called ASVspoof laundering database, and this database the purpose of this database was to evaluate the state of the art anti-spoofing methods to see how they perform in the presence of different kinds of noises or different kinds of processings. So again, the motivation was this incident where in 2024, President Biden's voice was sent to multiple residents in New Hampshire, right? The one unique thing in this deepfake audio was there was some noise added in the audio, and then if you have heard the audio again, you would see that there was some noise there that makes it that very sound like very real, like actual. It's like you the same noise that you would see in a phone scenario, right? So this kind of noise was purposefully added on top of this deepfake audio, and it actually tipped off many detectors. And but then over time, people were able to identify that this is a deepfake audio and it was generated through 11 labs. So this was the motivation, and uh, so what we did is we used ASVspoof from 2019 database, right, as our baseline database, and I'm going to skip these slides because I'll discuss these in the end. But what we did is we add different laundering attacks on top of the ASVspoof 2019 database. First, we added a reverberation attack on top of this database, and we added three different types of reverberations at RT60 0.3 seconds, 0.6 seconds, and 0.9 seconds. And then we created one database just for reverberation. And then we created a database with 5 different noise additions: white noise, babble noise, Volvo noise, street noise, cafe noise. And each of this noise is added at 3 different SNR levels. And then we created another database just for noise addition. And then we added recompression at 6 different compression rates. And then we added resampling attacks at 4 different sampling rates. And then we also added low pass filtering. We also passed all the audios through a low pass filter and then created this database. So overall, we got like 29 copies of this ASVspoof 2019 LA Eval database, which was around 1,200 hours of audio data. And then from here, once we have developed this database, we used anti-spoofing methods from 3 different categories. At the time, the SSL methods were not there, so we used like 3 different categories. One is traditional machine learning based methods, in which we have CQCC GMM, LFCC GMM, and then we have representation learning methods, in which we have LFC, CLC, and then OC softmax method. And then we have end-to-end learning methods, in which we have RONET2, ROGAT, ST, and ACES. So we took these 7 methods, which were kind of a state of the art at the time, but from 3 different categories, to see how they perform in this scenario. So what we did is we trained these methods on ASVspoof 2019 database, right? And then we evaluated these 2 databases on we evaluated these methods on 2 databases. One is ASVspoof 2019 LA Eval, which is a clean database, and then we evaluated it on laundered database, which is a noisy database. And we use equal error rate as an evaluation metric. So an equal error rate is lower the better. If your value is lower, that means you're performing much better. So so these were the baseline results, meaning the performance of these systems on clean audio, which is ASVspoof 19 LA Eval database. And from this, we can see that so like end-to-end learning based methods, they perform much better as compared to traditional methods. So then we evaluated on reverberation attack, and from reverberation attack, we see that the OC softmax is very it did degrade the performance, but it's very robust to the reverberation attack as compared to other methods which degraded like much more. For example, end-to-end learning methods, they degraded much more than the OC softmax. So then we evaluated on noise addition attack, and in the noise addition attack we have we see that RONET 2 performed much better. It did, again, the performance did degrade in the presence of noise, but again, for RONET 2 the degradation is not that much as compared to other methods. But overall, in the case of noise addition, you can see that end-to-end learning based methods, they performed overall better as compared to traditional methods. So then we also evaluated on recompression attack. In recompression, the trend was very clear, and end-to-end learning based methods, they performed the best. And even for 128K to 320K compressions, you see that the performance does not degrade at all. So yeah, the degradation was only occurring for the lower kind of bit rates. And then we also evaluated on resampling. So in the case of resampling, the trend was not clear. We can overall see that end-to-end learning based methods, they performed much better. But for 44, like when you use a 44K sampling rate, you will see that the performance degrades much more as compared to, for example, the other sampling rates in this scenario. So overall, we found out that end-to-end learning based methods, they dominate the baseline performance, as have been studied by other people as well. But under reverberation attack, we saw that this OC softmax method, it's much more robust to reverberation noise as compared to other methods. And we also established that end-to-end learning based methods, they outperform in the presence of additive noise attacks. And we also concluded that only on the lower bitrate compressions we see some vulnerability for audio deepfake, for audio antispoofing methods, but for other bitrate compressions we don't see much degradation there. So there was no clear trend for resampling attack there. So this work was published at IHMM-SEC 2024. And do you have any questions on this work? Okay, we'll keep moving forward. So next, so we recently participated in a safe challenge. So this safe challenge I already mentioned earlier, that this safe challenge was very recent, and we also participated in it. And what we did in this challenge was we tried to integrate multiple datasets together to do robust audio deepfake detection. So having discussed this already, we know that audio deepfake detection or audio antispoofing methods, they have certain limitations. They have limitations in training deployment mismatch. If you train a model on one dataset, they will not be able to perform much better on newer dataset or different deployment conditions. They are vulnerable to post processing, for example, audio transmission through some telephoning network, etc. They are vulnerable to social media platforms as well. If you upload an audio to some social media and then you download it again, and then you pass that audio to your audio deepfake detection model, you may not perform that well. And they are also vulnerable to intentional laundering attacks. There's some kind of deliberate noise addition or adversarial laundering attacks. And these methods are vulnerable to unknown scenarios, unknown languages, unknown TTS systems. So what this safe challenge was, they have these three different tasks. They have task 1, task 2, and task 3. Task 1 was they created deepfakes using latest TTS methods, and they do not process those deepfakes. Task two was they created the deepfakes, but they also processed it with some real world processing like compression, for example, resampling, etc. And task three was they added some kind of laundering attacks, which were like adversarial processings, like intentional laundering attacks, to see like how the submitted models perform in those scenarios. So the safe challenge was unique, and especially because they did not share any training data with the participants. This challenge was fully blind, meaning that no training data was shared, no evaluation data was shared. Right. So you have to develop a model that's able to perform well on some unknown scenario actually. So so they have this audio lengths which are like which can range from 1 to 2 seconds to anywhere to 60 seconds as well. So the first time they have these much longer audios as well in a challenge. So the first time where multiple languages were also introduced in a challenge, and they used the DT systems. And the challenge was to build a detector that is robust to real-world processing and laundering attacks, and it also generalizes to unknown TTS attacks in languages. So now, when we tried to develop this model for this challenge, we sat down and we decided, okay, so what kind of data set is provided to us, or what data set will our model be evaluated on? So they have shared a few descriptions of the data. They said that, so the real audio will be sourced from multiple sources. It will be multilingual, and it will have high quality conditions. It will also have low quality conditions. And similarly, the deepfake audios will be generated from state-of-the-art TTS models, and it will be so they will use open source TTS models as well, and they will also use commercial TTS models too. So they have shared this information already, and they have also shared that audio length can be of 60 seconds. And the data set is balanced between fake versus real on multiple sources. So the question now is, can we use like just one single data set to train our model and to have better performance? So the issue was that at the time when we were training our model for this challenge, each data set has its own coverage, as we have discussed earlier, like in the previous slides. For example, ASVspoof 19 is focused towards more traditional neural TTS methods, and it's only English and it has only clean conditions. Similarly, codec-based methods, for example, codec fake, has only codec conditions and it lacks other TTS systems. And some datasets will have acoustic mismatch. For example, some data has only lab conditions, and other dataset only have real-world deployment scenarios. So what we did is we tried to do like a dataset coverage analysis. We gathered like multiple datasets, and we tried to study those datasets and see like how what kind of properties those data have. So we found out that, for example, codec dataset has 15. They use 15 codec models to generate TTS methods. ASVC19, as we have discussed, they use 19 TTS models, but most of them are traditional neural synthesis models. MLAT, for example, this is a multilingual dataset, and they use like 54. So they have like multiple versions. So the first version was use 54 TTS methods, TTS systems to generate synthetic voice. And then we had Spoof Celeb. They also use 23 systems, but its focus is more towards noise. And Famous Figures focus was more towards protecting like famous people. So they created like TT systems for famous personalities only. So key TTS architectures in codec fake is speech tokenizer, for example, academic codec, and ASV19 there was WaveNet Aquatron 2. In MLAD there was VITS variants. In SpoofSelab they have used very latest TTS methods, and in famous figures we also use like much latest methods. So so when we performed this analysis, we found out that we performed this analysis on three different conditions, three different properties. We did that like what TTS method is used, whether it's traditional or modern, or it's neural codec method, or it's like very recent method. What kind of acoustic condition the audios have, and what is the diversity, how many languages are used. So we found out that, so we also evaluated other databases, but we found out that these five datasets, they are actually kind of very complementary to each other. So so that's why we try to combine these datasets together, which we'll discuss next. So once we have identified what datasets to combine, we then move towards finding out what SSL model is actually good to use for our submission. So we evaluated multiple self-supervised learning based methods on ASVspoof 19 dataset, and from this, and then we only did qualitative analysis, and then we found out that MAST frame and WaveLM large, they performed much better. As you can see that the green is original and the other colors are deepfakes. So green, so these two methods, SSL models, they are able to separate real from fake much better as compared to other SSL models. So from now on, we'll be using SSL, WaveLM and MAST frame only for our analysis. So this was the model architecture that we used for our submission. So what we did is we have a pre-processing pipeline in which if the audio comes in, we resample that audio to 16 kilohertz, and we use two different sizes of the audio. We either resize the audio to 4 seconds or 12 seconds, but I'll share that later, like whether we use 4 seconds or 12 seconds. And then we also did data augmentation. We applied raw boost data augmentation to all the audios, all the audio files in our dataset, and then we passed those audio files to a feature extraction module. So this module has extract features from WaveLM large model and MAST frame model. And the output of this SSL model goes to the ASIST backend, and the ASIST backend will classify whether the audio is fake or real, right? So, but we did that iteratively. So, so in our iteration one, we developed our baseline model in which we trained our model on just ASVspoof 19 dataset. And so this dataset only has 25,000 samples, right? And so this was our baseline one. And in iteration two, we started adding multiple audio files and multiple datasets into the mix, and we used ASVspoof data, MIALab data, MLADs, codec fake, famous figures. But in the iteration one and iteration two, we use 4-second audio split. We always cut the audio at 4 seconds in iteration one and iteration two. So next thing we did is in iteration three, we changed the audio length from 4 seconds to 12 seconds. So that's our iteration three model, and everything else is the same. In iteration four, now in iteration, if you go back to iteration two, so what we did in iteration two, let me just go back. In iteration two, we created we collected multiple datasets together, right? And then we randomly split the data 80-20% into training and validation. So by doing that, we have like 108K samples of training and 45K samples of validation. But in iteration four, we did strategic sampling, we did not just randomly split the audio files into 80-20 train and validation. What we did is we took, for example, if we talk about spoof celeb, we took 100 samples from 100,000 samples from spoof celeb, and we used like 50K of these samples are real and 50K are fake. And then we used MLAD. MLAD is, we sampled 60K samples from MLAD, but only 44K samples were used for training, and other samples are used for validation. But validation partition will have some unknown languages and TTS methods as well that the training partition doesn't have. So we held out a few TTS methods and languages in the MLAD partitioning, so that when the model is training, it should try to generalize much better while training. And then in the famous figures, we used a few speakers for training and a few speakers for validation. So overall, in this iteration, we have 200K samples for training, and we have around 56K samples for validation. Right, so these are the key iteration 4 changes. So the major changes in iteration 4 is we added spoof celeb dataset, which wasn't there in the previous dataset, and then we strategically split the training and validation partitions, keeping in mind that there should be some unknown languages and unknown TTS methods as well, and also some unknown speakers. Okay, so these were the results of our different iterations. So the top plot shows the performance of our submitted model on task 1. Task 1, if you remember, is the clean condition in which there's no processings involved. So our baseline performed, our baseline is just an ASIS model, and it got 50% balance accuracy, right? And then our iteration 2, we were able to achieve around 74% accuracy by adding those multiple datasets together. But the wave LM was around so this was for a wave LM, but the MAST was around 60% balance accuracy. And iteration 3, and from iteration 2 to iteration 3, we only changed the size of the audio. In iteration 1 and iteration 2, we had 4 seconds, but iteration 3, we had 12 seconds audios for training and evaluation. So in this case, we had some improvement, around 76% balance accuracy in this case. And then iteration 4, in which we did like strategic sampling, we were able to achieve much better performance, around 81% balance accuracy for task 1. For task 2, we had similar performance. Our iteration 2 was around 58.7% balance accuracy. So remember, task 2 is in the presence of noise when you have processings added to the audio file. So what's surprising is in this, when there are processings in the audio, we were able to perform better than when the evaluation data is clean. So we had like around 82% balance accuracy as compared to 81 balance accuracy. Is probably because we were doing like data augmentation as well, and we were also planning for noisy data. So task 3, we were not able to perform much better. So these were the laundering attacks. These were like intentional laundering attacks. So our iteration 4 was only able to achieve around like 49.6% for wave LM and 62% for MAST frame. So we evaluated this model, the model that we submitted to a safe challenge. We also evaluated this model on ATW benchmark, and so our iteration 1 was around 35%. So in this case, we are now evaluating using EER. So the lower the better. So our iteration 1 is around 35% EER, and if you look at iteration 2, we got around like 8.42%, and Same for iteration 4, around 8.42% for in the case of AVLM. So there was like a 76% improvement for in the wild scenario. So overall, we got second position in the private in the public leaderboard. We got like second position. In the private leaderboard, we were off by a few points, and we got like third position in that case. So if you look at like detailed into where our model actually performed well and where it didn't perform well, we so this first plot is the performance on real sources, real scenarios. And so this red line is where 60% balance accuracy, and we can see that the performance is not good for the German language or Arabic speech corpus, for example, here, and some Japanese shortwave, if the audio source is Japanese shortwave, and some phone home and Russian audiobook. So the data was very like highly multilingual, and we didn't even train for many languages. We trained for like 4 or 5 languages there. So this is the performance for generated sources. We actually performed like really good on different generated sources, except for just one, which is like Cartesia. So the good thing is, many of these TTS models we did not train the model on, but we were able to perform much better on these methods. But for Cartesia, we like had a much worse performance. So similarly for processed and for task 2 and task 3, processed and laundered, we performed really good, except for when there's noise. So this is kind of strange. Like we added noise in our data augmentation, but still we like didn't perform that well in this case. And the on task 3 laundered data, the performance was much worse. And so see, like if the card noise was like 0.5%, and then there is like this attack, which is you played the audio and then you attach some kind of reverberation, and then the environment was noise. You have like multiple attacks stacked together, in which we also didn't perform like that well.
Sorry,
There's
Hashim,
a
we're around 7 minutes over time now. So
I'm done. Yeah.
Okay, awesome. Yeah.
Yeah.
I guess before we end off, like I want to open it up if anyone has any questions for the papers Hashim discussed. Before we close off, feel free to ask. I wanted to ask, in terms of like, this is obviously a very cool work in terms of audio deepfakes. Do you think any of this might translate to, for example, in like education, text generated essays are a big problem. You also have like video deepfakes as well. Do you think any of these techniques could translate?
So essentially, like most of the technology is transferable, but then there is some things that problem specific. For example, in the case of audio, people have developed that if you generate a voice, you would have artifacts in either low frequency bands or high frequency bands, right? So and then you use those specific methods to capture those artifacts. But if you change the domain, right, so you would have maybe different kind of artifacts. So underlying technology is transferable. For example, I'm using, for example, graph neural networks, right, or some deep learning based method. In the text domain or in the video domain, they are essentially probably using the same technology. And also the problem is also the similar, right? For example, when I'm talking about you can add some kind of noise to the audio, or laundering attack to the audio, or some adversarial attacks to the audio. Those same problems translate to video domain as well, and to the text domain.
Makes sense. What would the noise be in the text domain?
That's an interesting question. I'm not too sure. Maybe you try to make the model not make sense. Like for example, so there are like some kind of so there are some kind of jailbreaking attacks that you can perform, in which the model will start if the model has some kind of safeguards on top of it, the LLM model, it starts giving you the prompts that that's not safeguarded. So yeah, so I don't have much experience with the text domain, so I'm not too sure. But I did listen to like one lecture, and they did mention that jailbreaking is one of the scenarios in which you can attack the LLMs.
Makes sense.
Yeah.
Cool. Any other questions? Okay, if not, thank you so much, Hashim, for your time. We are very excited to have had you for the talk. We're kind of want to get diverse opinions on like AI safety, and this is the first one we've done on like kind of multimodal AI safety. So thank you for walking us through your work, and hopefully in the future we'll have you back on again.
Thank you so much. Thank you so much for your time.
Take care.